This is the lecture for the Optics Chapter 25, the reflection of light mirrors. So, following slides are prep slides for class lectures. So, mirrors and reflection. The law of reflection is the easiest law that you can figure out, which is that the incoming angle equals the reflected angle, and you can see these here. All these images, by the way, are from the book. And this is important. It doesn't matter what kind of reflection you're having if you have a plane mirror, where this makes obviously sense right away, or if you have a curved surface. Notice the way the normal to the surface is in relation to the surface itself, that still the incoming angle is the same as the reflected angle. And if you look at any one of the other diagrams, that's the same thing, including diffuse reflection, which is on any kind of surface that is not a mirror. So again, keep that in mind. Law of reflection is always the same, and it applies to any kind of surface, even as we're getting, well, it looks different, but really it does apply the law of reflection. Reflective angle is the same as the incident angle. By the way, which other law is just as easy? What comes to my mind is Newton's third law, equal and opposite forces on two different objects as they're indirect. All right. Okay, here's where I want to show that with the move the tangent line. And okay, this is actually not right. It's not the optical axis. This is the normal to the surface and the normal. There we go. This is actually the optical axis here, right here. So here I move it here, and this here would be the reflective surface. This is the normal to it. And then when I put it on top of that, you can, well, you can see it before anyway, that incoming ray angle is the same as the outgoing one. And the same here. Let's see. Okay, that was actually the easy one. So this one here hits perpendicular onto the surface and is reflected. And this one here is a little harder to see. This one here from the object has a certain incoming angle and the same outgoing angle. And then this one the same as well. Notice that the normal is right in the middle between the incoming ray and the outgoing ray. And by the way, again, all these drawings are from the book. And then, oh, that's the same image actually. They just swapped object and image. Okay. So here's the image formation in a plane mirror. Here's the object, and show the image. And when I show these control points here, and I think these are arbitrary. I guess they even stay the same, but now I can grab this one here, and then the image moves around, and it's actually no big deal here. So I'm going to skip that one. I'm not going to show the gradient axis. You know, it doesn't show much. Show the incident rays, and then of course show the normals and the reflected rays, and we can see the law of reflection at work. And if I move this one here, you can see that incident angle is always the same as the reflected angle. Okay, now on the right hand side, what is happening is I take these green light rays here and extend them to the right hand side, and there they form the image. 2 from the top, which gives me that, 2 from the bottom, which gives me that. And this one is called a virtual image. I guess that's why we use a dashed line here, because it really doesn't exist. So the real image, there actually is an image that can be projected. A virtual image cannot be projected, so it's virtually there, but not really. And you actually have to have an instrument in order to look at it, which means you need actually an eye or a camera that projects that virtual image onto the screen, and it needs some optics in between, some lenses or mirrors, in order to project it actually onto the film or the retina. And that's then how you get an image that is being projected out of a virtual image. Of course, here we can also see that the size is the same of the image as the object, since it is a plane mirror. That'll be different when we looked at curved mirrors. Okay, this one here, I'm going to focus on this one here first. Actually, our textbook authors made a mistake in this image here. It says the image of yourself in the mirror is also reversed right to left and left to right, and I'm saying no, it's not. See how it's fixed in the second image? This hand is on the right. This one is still on the right. I understand that the mirror is doing something, but that's not it. So let's look at this one here. I took a photo of my son, Benjamin, and he's looking in the mirror. You see his mirror image here, and I put directions on here. And instead of calling these left, right, up, down, and so on, I will just use the cardinal directions. So north, south, west, east, and these are borrowed from astronomy. Zenith is straight up, nadir is straight down. So for the next minute or so, we totally abandon left, right. We're just going to use these here. Okay, Benjamin in our house is actually facing due south, okay, which means that he's pointing to the east, right? If south is forward from his point of view, then east is over here. Again, notice how I try to avoid these other words. So he's pointing east. Notice his mirror image is also pointing east. Now, the arm on the other side that you don't see here is on the west side. Notice that the arm in his mirror image is also on the west side. All right. Notice that his head points towards the zenith, while his feet point towards the nadir. So everything is peasy. The reflection doesn't do anything. It doesn't change anything. But then again, it actually does. And here's the clue. He is facing towards, he's facing towards the south. That's what I said earlier. But the image, notice in which direction the image is looking. The image is facing towards the north. And that is what the mirror is doing. It turns front and back around. Now I can use these terms left and right again. His image is pointing to the left, but he himself is pointing to the left, but his image is also pointing to the left, and that becomes again clear as I call these east and west and then swap back later. And again, we get this illusion because it's actually the front and the back that are swapped. All right, let's continue. This one here is the equation for spherical mirrors. So the focal length based on the curvature is 1/2 r, the radius, and you can see it here in this drawing again from the book that the focal length is at half the radius. That can be derived. Then there is what's called the mirror image, and the plus and minus, by the way, goes for concave mirrors versus convex mirrors. Then there is the thin lens equation, which can also be derived from these principal rays. I'm going to talk about these principal rays here in a little while. I'm not going to show the derivation, but here it is. This one is very important overall, one of the two most important equations in this basic optics lecture. So this one here is the mirror equation. By the way, when it comes to lenses, it is the exact same one as the thin lens equation. It relates the object distance, which is here, object to reflecting surface, and the image distance, which is here, reflecting surface towards image, with the focal length, which is right here. Again, this distance here. Actually, always measured from the reflecting or refracting surface. The magnification equation is here. We use it a few times, but not a whole lot. This makes sense here that the height of the image divided by the height of the object is the magnification. And then this one here turns it around. And this one here actually naturally introduces a negative. While these two numbers, as they're positive, there needs to be another negative, and the negative simply means that it turns it around. So the image is upside down, as we would notice in a concave mirror. By the way, only if we're far enough away. A concave mirror can actually be used as a makeup mirror, and you would have to be relatively close to see yourself upright. If you move far enough away, you will actually see yourself smaller. I'm sorry, upside down is what I meant to say. Um, I think also smaller. No, no, larger, I believe. Um, I think it's smaller. All right, let's go ahead. Here's a sign convention that comes in handy. This is actually from my lab on Gauss thin lens equation. It applies to mirrors and lenses, as I said, and we have these positive focal lengths here for concave mirror, respectively convex lens, negative for convex mirror, negative for concave lens. And then you have object distances, you have image distances for real and virtual images, magnification, and so on. I will talk about more about what a virtual image is when we get to lenses in the next lecture. All right. Ray tracing. So again, this image is from the book actually. So ray tracing, we like to use three principal rays. So here is the object. One of those principal rays is that it goes parallel to the optical axis. It's being reflected. And again, that's the law of reflection. And it will pass through the focal point. I'm not showing the derivation here or the proof, but you can try it yourself and you will actually figure that out, that that is the case. Um, Another one is that goes through the focal point, hits the surface, and comes back parallel to the optical axis. Of course, these two here will intersect at some point, and that's where the image would be formed. There's a third principal ray, which is this one here, which if you extend the line from the object through the center point, where you have the radius, it hits the mirror where the angle with the normal is 0 degrees, so it comes right back, and again it intersects over here. And these are what are called the three principal rays that you see here. It can be done in a different way. This one here, this is from a paper that was submitted to a physics teacher from professors in Thailand. That's why you have it down here in Thai. And they were saying, well, you could use others as well. You just have to do more work, such as this ray here that is neither going through the focal point, nor is it, or here, let's look at the mirror here. These are the lenses. So let's look at this concave mirror here. So this one here is not parallel to the optical axis, nor is it through the focal point or the center, but it hits in any one angle here. It comes off, and what you do actually is you look at not at the focal point, but at the focal plane. You take this ray here, you push it down parallel up to here, and now you apply this line here where it then intersects. And sorry about my cell phone in the background. All right. We really don't have to know this here, but I just want to show that while you find in textbooks these three principal rays, any one of them would work. These are just much easier to apply than these. So here's image formation by concave and convex mirrors. We have the principal rays, which are the ones that go through the focal point and then become parallel. The one that is parallel and then goes through the focal point, and the one that goes through the center point and is reflected right back, even though that does look a little bit funky. Talking about funky things, there's another one. Of course, these rays should be reflected on the mirror surface, but notice they're actually reflected on the y-axis. Oh well, the person who made this one here, I'm sure put a lot of effort into it, and that was just something that they couldn't fix. For example, if I flex this mirror here, you can see that even more pronounced what's happening with these reflected rays right here, instead of the surface. Oh well. And this one actually doesn't look perpendicular. Ooh, that's a little bit off then. That's what it is. Anyway, what I just showed, flexing a mirror, actually we can't really do that. So a mirror is fixed in the way it looks like. And when I choose a different mirror, I'll let you know. So here I chose conveniently the focus at being 8 centimeters. Ignore the negative. I know it's on the negative axis on the negative side of the x-axis, but when it comes to sign conventions, when it's on the side of the mirror where the object actually is, that's considered the positive side. Okay, then again, this one here is also, so the focus is 8 centimeters, and this one here is 12 centimeters. That's the object distance. The numbers work out in such a way that if you do 1 over 8 minus 1 over 12, and then invert that again, you actually come up with 24, and that's what it says, rounded numbers here. Change the object distance, that will change the image distance as well. So here you also notice that the magnification gets quite larger the closer we get to the focal point. So again, when we do 1 over 8 divided by 1 over 9, apparently we come up with 1 over 70. So the image is way, way out there. When we go to the closer and closer to the focus, by the way, I also should mention that the image is inverted. Again, it's totally off the screen. And the real image, it's a real image as well. And when I get closer and closer to the focal point, actually it becomes at infinity, and it's really not there. I guess it doesn't make the transition exactly here. When I put it on the other side, inside the focal length, there it is. It's an upright and virtual image. So again, virtual image cannot be projected. You would actually need something else like the human eye or a camera lens to look at that. You also see the principal rays here. So the parallel one that goes to the focal point, the one that goes to the focal point, which is not extended here, becoming parallel, and then the one through the center that is going straight through, respectively straight, reflected. I'm going to move this one over here because we really hadn't seen the the image yet. So I'm going to put this one here closer. I'm going to change the mirror actually. You cannot really do this with a mirror. So I'm going to change it here to 4 centimeters. And there we can see the real image. So here we have, for example, a focal length of 4 centimeters and an image distance of 10. So 1 over 4 minus 1 over 10 equals apparently 1 divided by 6.67. All right, let's look at the convex mirror. The convex mirror, we're pushing the object over here. It doesn't allow me to turn the the mirror the other way. So I'm just going to do it this way here. That's what it says actually in the instructions. So here now I would actually have a focal length of this convex mirror of negative 4 centimeters. And the object here would be at 8 centimeters. That would be a positive number. So I'm going to have 1 over negative 4 minus 1 over 8, and that apparently is 1 over negative 2.67. We get a virtual image because it cannot be projected, and it is upright. And again, if you look at it, it all makes sense. You see the principal rays, you see the mirror equation, respectively, thin lens equation at work. All right, this person here also put a lot of work into this. So this is on Desmos. And so here again, we also can change the focal point. Okay, actually not. Oh yeah, I can change the radius over here and you will see that the focal point changes. Again, you can't really do this with a real lens. You actually would, I'm sorry, real mirror, you actually would have to choose a different mirror here. So let's say I have a radius of 100 centimeters, then my focal point is at 50 centimeters. And then again, we see the principal rays and here the object and here the image. And again, we would come up with correct numbers. So for example, we would have focal length of 50 centimeters, 1 over 50 minus 1 over 81. And when you plug that in, apparently you come up with 1 over 130. This can be made into a convex mirror. There it is. So here we have, again, the object. So let's say we have a focal length of, 125. I'm going to pull it a little bit back so we can actually see the focal point. Or at least I was hoping so. But there's the center. Oh, there's the center, and there's the focal point. So negative 50 centimeters is the focal point. Here's the image. And again, we see the principal rays. And so, for example, here we would have now 1 over negative 50 minus 1 over 100. Remember that this one actually is a positive number. And that apparently comes out to 1 over negative 33. That's where the image is. And I encourage you to play around with these. I posted them in the PDF as well, these links, and they're actually relatively easy to Google. Just type in mirror applet, and I did come up with the O physics. Respectively, I typed in Desmos mirror, and I came up with this one. This particular image here, which again, this one down here is actually the same one. It's just that they swapped object and real image. I'm showing this to you for the 4th time now. So let's actually see if they applied the numbers correctly. So that's why I got the ruler here. And I measured prior that the object distance right here is 4.2 centimeters. And I think we can already see that right there, 4.2 centimeters. Now I'm going to look at the object distance. That comes out to 10.5 centimeters. There we go. Which then I'm going to plug in here. At least I try. There we go. There it is, 10.5. And then I calculate. And when I do that, these two fractions, 1 over 4.2 plus 1 over 10.5, I come up with 0.33333 repeating, which means that over here, as I also have 1 over f, I take the 0.333 repeating and invert it again. And of course, that comes out to exactly 3.0. By the way, this thin lens or mirror equation linking the object distance with the image distance and the focal length is in the same manner as adding resistances in parallel. So 3.0 is what I came up with here for the focal length, and we can see that already in the drawing. That is definitely 3.0 centimeters, which I'm going to write down here because this is what I measured. So there you go, and I guess that's a check mark that indeed the drawing they gave us is correct. All right, let's see. Following problems pages are prep slides for problems done in class. I'm only going to do one because the others are already posted in other recordings. So here we go. Chapter 25, problem 17. A concave mirror has a focal length of 42 centimeters. The image formed by the mirror is at 97 centimeters in front of the mirror. What is the object distance, DO? Notice that my scale is different here. So even though I know this one here says centimeters, but let's assume that these are actually decimeters. So here we have 97 centimeters. Again, the scale is different from the other one because I gave us different numbers. So 97. And then we can see that, always tries to turn this ruler here. And we can see that this one here is 42 centimeters. So I'm going to put this one over here. And then as I subtract 1 over 42 minus 1 over 97, I come up with 0.0135, which I invert, and I come up with 74 centimeters. So that's what I'm going to plug in here. And that would be my object distance, which means I have to Measure this one here, 74. By the way, I paused the video and calculator on the side, so I'm not taking time away from that. So I get an image here. I'm sorry, that's the object. This is actually the object. This one is actually the image. And then the magnification equation, which I didn't write down here, would tell me that I have, so the magnification equation actually says that the image distance 97 over 74, which gives me somewhere around 1.3 or so, but the image is actually larger than the object, so I would have to make this one larger by about a factor of 1.3. Okay, that's a little bit too much. That probably cuts it. Yeah, that's pretty close probably. And then because of the minus, it actually turns it around, which means this one ought to be over here actually. There we go. Or I could have turned the object around either way. And by the way, do I actually have the, 74 is actually here. Whoopsie. It's a little bit off. And that would be it for this lecture on chapter 25 for mirrors.